All right, so we want to derive these equations. We start out with the governing equations here for temperature and mass fraction. And we assume equal diffusivities, Lewis numbers equal to 1 for all species. And so is equal diffusivity for all species and thermal energy. That is not necessary to make that assumption, but if you don't make that assumption, the equation get a lot more messy. If you're ever interested in, looking at this for differential diffusion, we have a paper where we write out, all these equations without making these assumptions, but making these assumptions makes it a little simpler. Okay, so temperature equation is, so you see on the left-hand side, they look the same. Then on the right-hand side here, you have chemical source term for the temperature and also for the species. And then here for the temperature, there are two more terms which you might as well forget, for this purpose. One is a radiative heat loss term, is this one here. And then the second one here is the is just a term that that gives you the change of energy here for compression, so the compression work term. So that would just be, so the P here is just the background thermodynamic pressure, which means that's the pressure change you get, for example, in internal combustion engines. So that term is important for that. But for the purpose here of looking at these equations, forget about these terms, just look at these. Okay, so here we also want to consider now mixture fraction. You see mixture fraction has the same terms here on the left-hand side. On the right-hand side, 0 has no chemical source term. That makes perfect sense because we said the mixture fraction, that's kind of like the equivalence ratio. And the equivalence ratio, of course, it doesn't change with chemical reactions. So this is the set of equations we have. And so the, well, again, this is what I just said. That this has no chemical source term. So now let's look at this. You have a fuel, let's say a jet flame here, a fuel here in the center, oxidizer here outside, mixture fraction here in the center is 1, outside it's 0. That's just how we defined it. And then there will be a stoichiometric surface here somewhere in between these two. And stoichiometric is where you have all the combustion happening now. And so this is what we want to do. We want to attach a coordinate system to the surface. We want to assume that locally now, at this point in time, the coordinate system x, y, z, or x1, x2, x3, it's attached to the coordinate system. And we want to assume that in this point where we do the analysis now, the x1 coordinate is normal to the surface of stoichiometric mixture, okay? One thing I should say, maybe this is the first time we do this here, these are the equations, of course, but these are for now we always looked at one-dimensional equations. These are equations now in three-dimensional space, right? They're the full three-dimensional equations. We don't make an assumption that anything is one-dimensional. We just look at the three-dimensional space. Okay, but we want to fix the coordinate system like I just said. And then here's what we do. We want to, so x1 is normal to the surface of z equal to z stoichiometric. And then x2 and x3, they are, of course, then in the surface of stoichiometric mixture. So now this is what we're going to do. We want to do a coordinate transformation such that we replace x1 by mixture fraction. That is interesting because we, in a sense, x is a dependent variable. Sorry, x is the independent variable, and z is actually one of the dependent variables. But we replace now one of the independent variables by a dependent variable. Okay, so we replace x1 by mixture fraction, and because x1 is normal to the surface of stoichiometric mixture, x1 points in the direction of the gradient of mixture fraction, okay? And so the mixture fraction and x1, they point in the same direction, really, okay? The change of mixture fraction and x1, they point in the same direction. So really what we do by this coordinate transformation is just a stretching, okay? We stretch the x1 coordinate into the z coordinate so that it just measures the flame, you know, in the right length scales. That's what we do. And then x2 and x3, they stay the same, but for the matter, for the sake here of the coordinate transformation, we give them new names. X2 and x3 now, we call them z2 and z3. And the time we call tau, okay? Why do we need to give them new names if they stay the same? Now, this is just a mathematical reason. Why do we need new names when we do a coordinate transformation? Why can't we just leave them x2 and x3? No, not just for convenience. There's a mathematical reason why can't we, if they're the same after the transformation, why can't we just leave them the same? Why do we need to touch them? We can just transform this one variable and not the others. Why can't we do that? That's a subtle but it's a very important point. Z is a function of the coordinates. It could be, usually the new coordinate and the old coordinates, they're a function of each other. Otherwise, I wouldn't have a transformation rule. These coordinates, x1, x2, x3, they're not, in a sense, they're not independent of each other. They are defined within one coordinate system. What you define is not three independent variables. You define a coordinate system. That coordinate system is t, x1, x2, x3. Okay? Why is that important? Because if I write dt by dx1, this has a very clear meaning only if I know x2 and x3. Okay? Because this means really x2 and x3, this is the change of the temperature with x1, but keeping x2 and x3 the same. x2, x2. Okay? So a partial derivative is only defined in the context of a whole coordinate system, not in terms of just one single coordinate, right? So that means if I introduce a new x, if I do a transformation of x1 into a new coordinate, even if the others stay the same, I give them new names because they define a new coordinate system. I don't replace just one of these. I say x1, x2, x3 goes to z1, z2, z3, and tau and t. We sometimes when you see analysis like this in a paper or so, sometimes it's not done rigorously. That's fine. I mean, you know that you really give them new names all the time, especially for the time. We don't always do this, and that's okay. You just have to keep in mind that this time here and this time here, they're very, very different. D by dt here means at one point in space, d by d tau, or let's say I call this also t, d by dt in this system means at a constant mixture fraction, at constant z. Okay? That's different. That might be a point that moves in space. Okay, so keep that in mind, that we always need to think about the whole system. Good. So if we do that, then you see d by dt, so t is equal to tau. I mean, it measures the same time. But d by dt is not the same as d by d tau because it's defined in a different coordinate system. And so the transformation rules then are given here. D by dt is this. You see it depends on the z. D by dx is this. And d by dx alpha here for, so this d by dx1 and d by dx2 and d by dx3, they're this. Now I just realized I used alpha here as an index. you know, that goes from 1 to 3, and then I used alpha here as an index that goes from 2 to 3. So, you know, this should be beta, let's say. Okay, it's not the same. Anyways, let's say now you can introduce all this in the equations, and then for the temperature equation you get this, and then you see here you get, you know, this time-dependent term, and then you get Z2, Z3, you know, and all these things. So you get a lot of individual terms. Good. So now we can think about what do we do with this? I mean, we want to, I mentioned this earlier, we do a coordinate transformation. We did this now, and now we want to do an asymptotic approximation. The first thing we can do is, rather than going through the asymptotics or whatever, we can think what would happen if the chemistry was infinitely fast. Let's say the chemistry was infinitely fast. What would happen then? No? Well, in the derivative, yes, but not in the values. But that's not the point. I mean, what I get a simplification. You get a nice simplification if the chemistry is infinitely fast. The chemistry is infinitely fast. Let's say Burke-Schumann was Burke-Schumann solution was infinitely fast, plus assuming complete conversion, but let's assume this for now. What happens then? The Burke-Schumann solution was a function of what? Of mixture fraction. It was a function of mixture fraction of nothing else. Okay? If you assume infinitely fast reversible reaction, that's equilibrium. Also, the solution is only a function, let's say, of pressure, of enthalpy or whatever, and the composition. Composition is Z. Okay? So, the solution is only a function of Z, nothing else. So what does that mean for this equation? It means it cannot be a function of Z2, and it cannot be a function of Z3. Or we look at it here in this coordinate system. It basically means at Z everywhere at Z stoichiometric, I get the exact same solution, the solution for Z stoichiometric. Okay? And Zx2 or Z2 and Z3, they change along the surface, but the solution does not. So this means for infinitely fast chemistry, all the terms d by dz2, d by dz3, they all go away. So we can look at what's left over. This one here would be left over. This would be gone, 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 gone. This one here would be left over. And this gone, 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 and that's it. Okay? And then the right-hand side, of course, stays. So you have this term, you have this term, and then you have the right-hand side. So then it's very simple, actually. That's an interesting way of looking at it. Actually, this transformation was first done by Bob Bilger, assuming infinitely fast chemistry. He just then came up with this term, and he had some very nice conclusions drawn by this. So this is the term that says. So this is the time-dependent term, and then the only other term that remains here for infinitely fast chemistry is this term. So it's this term. So that term is very important, and it turns out, and now we don't need to go through the all the math, but the asymptotic approximation that we make is to say, look at this thing. We said stoichiometric, that's basically the interface between black and white here, okay? Now, walk along this interface, what are the changes? The changes, there are changes, but they're very small, okay? You see the temperature or the luminosity of this color here, it changes a little bit, but not very much. Okay, that would be if I move into the Z3 or the Z2 direction. If I move into Z direction, that would mean I'm at the interface again, and now I move normal to the interface. If I move normal to the interface, the changes are tremendous. They're huge. Okay, dt by dz in that direction is huge, whereas the changes in the other directions, they're very small. Okay, so the asymptotic approximation then is to say changes in direction of z, they're very large. Changes in direction of z2 and z3, compared to that, they're small. And so we drop, asymptotically, we drop all these terms. And that is exact in the limit of infinitely fast chemistry. Okay? And it's still a good approximation if the chemistry is not infinitely fast, but it's relatively fast. Okay? Chemistry needs to be relatively fast, and then it's a good approximation. Just like for this thing here. It's not infinitely fast, but it's relatively fast. So that is the equation then we get. We just have this kind of diffusion term here left over, and the diffusion term and the time-dependent term, they balance here the chemical source term. And we said forget about these two terms for now. So the time derivative here, that's important. Anytime you have slow processes, like radiation is a slow process, pollutant formation is a slow process, then you need this time-dependent term. But you know, very often this time-dependent term here is also very small, and then you see you just have this term here balancing the right-hand side. Now, what you see here, so this just gives you some details on the asymptotic approximation here, and really the assumption is the Damköhler number is relatively large, not infinitely large, but relatively large. And then you come up with this set of equations here. Now, if you look at this, you have this term here, dz by dx alpha squared. And what does that mean? So dz by dx alpha squared, that by definition is what we call the scalar dissipation rate. We will see later on why it's called scalar dissipation rate. This term, also the same term, appears when we talk about turbulence in the scalar variance equation as a sinc term of scalar variance. What is a sinc of scalar variance? We'll see that corresponds to the rate of local molecular mixing. Okay, so this scalar dissipation rate, that's the rate, even in a turbulent flow, that would be the rate of small-scale molecular mixing, when fuel and oxygen really come together. Yes?
And you just mentioned that radiation is a slow process. Can you clarify about it?
Yes. So if you look at this flame, you have a radiation here, right? If radiation was a very, very fast process, you would lose all the heat right here, and this thing would extinguish right away. Okay? But it doesn't. But it extinguishes somewhere up here. So this is not extinction, it's just mixing with the air. But if you had a larger and larger flame, then at some point it will extinguish here in the top. For example, if you have a big pool fire or something, like a huge fire, then you see lots of smoke coming out, this because it extinguishes. So it takes about, you know, whatever, it takes a long distance or a long time for the flame to extinguish because of radiation. That's what I'm saying is a process that's relatively slow compared to the chemical timescales or even the flow timescales. Okay? Okay, yes?
You said that in the limit of infinitely fast chemistry, the Z2 and the Z3 fluxes go to zero.
Mm-hmm.
How do we do that? I mean, how does
They don't go to zero. So the question was why I said in the limit of fast chemistry, the fluxes in direction of Z2 and Z3 go to zero. The changes really, because the gradient is not a flux. So let's just say the changes in this direction, they don't go to zero. They're just very small compared to the gradient in the Z direction. Or if you say for infinitely fast chemistry, they actually go to zero because, I mean, it is relatively simple. If I have a jet flame like this, and this is the surface of stoichiometric mixture, okay, and I say in equilibrium, the temperature and the mass fractions, they are a function only of the local pressure, the local enthalpy, and the local composition, okay? Then this here, of course, is the same as Z. Then I fix the pressure, I fix the energy. Then this is only a function of Z, which means for a given Z stoichiometric, you get a certain composition and a certain temperature, which means these values, they don't change along the surface, okay? So dy by dz2 has to be 0, okay? Yes?
So in the endpoint fast chemistry, would you say the scale of dissipation is infinity?
No. No. No, but no. And I'll tell you why. So, let's see. So, the Damköhler number, we said, is a ratio of a flow timescale over a chemical timescale. Okay? Now, we're going ahead, but ahead of ourselves. But the flow timescale, actually, for diffusion flames, you see that this quantity here, the scalar dissipation rate, this quantity here, the scalar dissipation rate, it has units of 1 divided by second. Okay, this is meter squared per second. This is meter squared, so it's 1 over second. That's the inverse of a time scale. And so here we can say this is then 1 divided by Tc and the dissipation rate. Okay? So what you're saying is, so fast chemistry would really be very large Damköhler number, because when we say fast or slow, we always mean compared with something else, right? So here we talk about the flow time scale. So large Damköhler number would mean very small dissipation rate, okay? Because if you have very slow mixing, then the chemistry is fast compared to that. But even, and that's why I was hesitating, but even if you say very small dissipation rate, that still doesn't mean fast chemistry. Because what is small? Small is always compared to something else. If you say the dissipation rate is much, much smaller in the chemical timescale, or the inverse of the dissipation rate, much, much smaller in the chemical timescale, yes, that's fast chemistry. Okay? So if this product is small, then that's fast chemistry. Okay? Okay, so I talked about the dissipation rate. So it's this thing here. Why does this appear? Why does it appear? I said it's the local mixing rate. That is, of course, very important. But so look at this here. I just want to show you why do you get this parameter dissipation rate, or what does it physically mean? Here, this is in physical space, and we said if you have a high strain rate, then you get very large gradients, and you have very strong heat losses and all of that. Okay, high gradient heat losses. Now we wrote the equations in terms of mixture fraction, and you see here in terms of mixture fraction. Basically, for all the different cases here, the gradients are always the same. The dt dz is roughly the same for all three cases, whereas here there's a huge change. Okay, so the gradient with respect to the gradient, the change of temperature here with respect to spatial coordinate, is in these equations expressed as the change with respect to z times the change of z with respect to a spatial coordinate. Okay? So when you go back to this, what the dissipation rate does here really, or here, it tells you how large, so this here doesn't tell you how strong the gradients are in physical space, and this here tells you how strong are the gradients in physical space, then multiplied by or this tells you the gradients of mixture fraction in physical space times the gradients of temperature with respect to mixture fraction. So what this parameter dissipation rate just does, it brings back in the information that one profile was very strained and the temperature, the heat losses were very strong and the other one was not. Okay? So this here really represents the effect of the flow field on the flame structure. Okay, so that's the dissipation rate. Dissipation rate is very important here, inverse of characteristic time, and it is related here to this diffusion process. Okay, so the other thing you see here is that if chi goes to 0, if this dissipation rate goes to 0, then this term here goes away, and you see you get the equations for homogeneous reactor. Okay, so that limit is incorporated here in these equations. So now, if we solve these Flamel equations, the first thing you see now we have a parameter here, external parameter. So what in the counterflow flame was the strain rate. That's now in these equations the dissipation rate. Okay. Or you could think of it like this. If you look at a counterflow flame, then you have the strain, and the strain is basically a feature of the velocity field. The velocity field will then change the scalar field, and the scalar field then, you get more or less diffusion in the scalar field. The dissipation rate is already a characteristic quantity for the scalar field. Okay, so you could think of it like this: the strain, if you increase the nozzle velocity, you increase the strain. Then the strain increases the scalar dissipation rate, and the dissipation rate then has an effect on the chemistry. Okay, in these equations. So these equations here, they describe a very similar thing as these equations we had earlier for the counterflow flame. Only that for the counterflow flame, from the beginning on, we said we look at a one-dimensional system, and here we didn't say that. We said this is a full three-dimensional flame, whatever turbulent flame. We just look locally very close to the reaction zone, and then we came up with this one-dimensional flame structure. And then the second thing is, the second difference is you could say these here are closer to the chemistry because the strain changes the scalar field, and the scalar field then impacts the chemistry. And this quantity, this parameter here, is already the parameter that signifies how the scalar field looks like. Okay, so these are some results here then. There's a mistake here in this. I have this error since like 20 years. And every time I think I should change this. And every time I come to this slide again in whatever course I give, I see the same mistake. What's the mistake? You mean this? Well, I could write it as Damköhler number, but it's easier to write as dissipation rate because the dissipation rate is really what I specify in the solution of these equations. I specify a value. I say it's 5 or 10. I didn't put it here, but that's what it is. Oh, maybe no. I actually plotted this from here, so I don't even know exactly what the value is. I just say this is how it's changing. What's the mistake? Arrow should be the other way, right? We said high dissipation rate is high gradients, is stronger heat losses, so you get a lower temperature here. So again, this is what you get here. This here, isn't that the same? A similar picture than what we looked at earlier. This here is now propane. Earlier we looked at methane flame, and then this is a propane flame. Interesting, I'll tell you why. So I probably had this here first, and then I was going through the lecture before I submitted the slides here to Lilian, and I came to this first point where I showed you this for methane, and I thought it would be nice to have a picture like this. And so I made it up for methane, and then 10 minutes later I saw I have it already for propane. So it's same picture just for propane. But again, you see low strain rate here. You get very broad profiles, and high strain rate, you get very low profiles. This is close to extinction, 950 for methane earlier was like 500 something. So you see that is a parameter that's different for the extinction strain rate. That's a parameter that's different for the different fuels. Okay, so now we can also here, we can solve these flamelet equations for different values of the dissipation rate. And then we can also look at the maximum or the stoichiometric temperature as function of dissipation rate. And then you see you get this, this S-shaped curve. So all of these here are solutions to these flamelet equations. And what you see is, first of all, there's a region where you get multiple solutions. That's not surprising because we said this is a very strongly nonlinear system, but for a dissipation rate here of this value, you see you can have one solution here, one here, and one here. Turns out that this intermediate branch that you see here, that's unstable. It's not stable. It's a steady state solution, or it's a solution to the steady state equations, but it's an unstable solution. So if you have a solution, this takes this solution here, and you make the temperature slightly higher, then bam, it would move up here, and if you're here, make it slightly lower, then it would go to the lower branch, okay? But what you see here is you increase the dissipation rate, the temperature gets lower, 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 until you get a point. There's no burning solution at higher dissipation rates, and then you get quenching here. And then you would be at this lower branch, but now you decrease the dissipation rate again. It doesn't ignite automatically. Why? Because now the temperature is lower than the inner layer temperature. You know, nothing's happening. It's like my my desk here, a wooden desk. It doesn't burn. This has fairly low dissipation rate, let's say, but you know, it doesn't burn. So now you need to decrease the dissipation rate up to a certain point. If you get lower than a critical point here, again, then you would get autoignition. Okay, it would ignite. How large is this value? We saw earlier, so this here, this value here for a methane air. So take methane air mixture, or this here, propane. Let's say propane. Propane air. Okay. So I do this. Okay, and we can wait until the gradients get small enough that it ignites. Okay. So I turn this off now, and now see the gradients get smaller, smaller. It doesn't ignite. You see, it doesn't ignite. Why? Because this point here is 10 to the minus 15 or whatever. This is very, very small. And then the ignition delay also would be very, very long. Okay, so this doesn't ignite. But if you increase the preheat temperature, like in a diesel engine, this is exactly what you have. If you inject in a diesel engine, in the beginning, the gradients are very, very high. Okay, so the dissipation rate is very, very high, and then it mixes. The dissipation rate gets lower, the gradients get smaller, and then bam, it auto-ignites. Okay, that's exactly what you have in a diesel engine. You typically start up here, and then it ignites. And well, quenching. How can I do this? I mentioned this earlier. What does it mean? What does it mean increasing the dissipation rate? It means increasing the local gradients. How do I do this? By imposing local strain or by decreasing the flow time scale. And I can do this here in my little example. I can do this by just imposing a velocity like this. And if I do this, I increase now the dissipation rate. I increase it more and more. I increase it more. Well, at some point it extinguishes, okay. I do it with this here. Okay, this, I increase the dissipation rate, look, gone. Or you can also do it like this, gone, okay? So, so blowing at a candle is nothing else than increasing the dissipation rate up to the point where you get quenching. Okay, that's what you do when you blow at a candle. So, so this is important. It's interesting that you get these multi-valued solutions here. Okay, so that's the flame equations. Flame equations then they tell you something about the local structure close to a flame. Let's see, I added this morning, just 2 minutes before the class. There's one more thing that's very interesting about these flame equations, because you can use them really to analyze experiments also. If you look at these equations, then you see, so forget about these last two terms here, and then let's assume things are in steady state. So it's not steady state, just this flame structure itself is in steady state, which means you can neglect this dt by dt term, and you have just this term is equal to the chemical source term. And now what's interesting is that, so if the chemical source term is positive, okay, chemical source term is positive, this implies, you have a minus sign here, this here is never negative, it's a positive definite value. If this here is positive, it means this here is negative. You have negative curvature. If you plot mass fractions as function of mixture fraction, then the curvature tells you what the chemical source term is. Okay? So you can do that with your experiments. I took some I took experiments here. This is from Rob Barlow at Sandia. This is the Sandia Flame D. Many people know this. This here is from a simulation we have done. But look at this. This is temperature. Temperature, the stoichiometric mixture fraction is 0.3 something, or 0.4, something like that. This is the highest temperature. Here's mixture fraction 0, mixture fraction 1. In this flame, actually, at mixture fraction 1, the fuel stream has some air in it also. That doesn't matter for us, as we said last time. But you see here that you get a negative curvature here, or positive negative curvature, which means you have a source term here. You have a chemical source term here. And here it's even stronger. Look, for example, at down here we have NO. This is NO. And this is interesting, or take this profile here. This is NO. You see, this is where NO is formed because of the curvature. You see on this side here, curvature goes the other way. This means NO is consumed at that point. There's some consumption of NO here on the rich side. And this is where it's produced. And you see here, it's just a linear slope. And linear slope means it means the source term is 0, right? It means the source term is 0. So linear slope means the second derivative is 0, means source term is 0. Okay? So with these equations, you can really look at all of this and make a lot of sense out of it. You see OH, this OH is formed here. It's consumed here. This does not mean just transport. Curvature means always chemical source term. Chemical source term here. This is where CO is consumed right here. It's formed right here, consumed right here. You see on the rich, nothing happens. Linear means chemical source term is 0. Okay? So if you have mixture fraction, and you can plot experimental data as function of mixture fraction, you can make a lot of sense out of what you see. Okay, so that, so take this with one little grain of salt. When we look at this here, then this temperature, and you see this curvature here. Curvature means source term, we said earlier. not exactly right, because in the temperature equation, you have one additional term, which messes things up. And so you have two additional terms. You have this term diffusion by energy transport by species diffusion, or sometimes called the enthalpy flux term. But then also there's one additional term which we neglected here in our analysis, which is because of the changes of CP. CP changes as function of temperature, and that really causes the curvature here in this temperature profile. So that's what I said earlier. For temperature, one has to be a little more careful, but species, there's no other term here in the species equations. And because of that, for species, you can really say all the curvature just comes from chemical source term. Okay. Okay, any questions about this? Yes?
When you consider the infinitely fast chemistry, then omega is 0 everywhere except at the curvature point. So, is that true?
Yes. Basically what it is, that's an interesting question. Because when we looked at the Burke-Schumann solution, it looked like this. Y fuel looks like this. Okay? And the temperature looks like this. What does this mean? Infinitely large curvature, which means fast chemistry. Okay? That's exactly what you see. From this, you see exactly how fast the temperature is. If the curvature becomes infinitely large, then the chemistry is infinitely fast. Very simple. Okay? Okay, so now the dissipation rate here, actually that's a function of mixture fraction also, and so I just want to, because the gradients of mixture fraction are a function of mixture fraction itself, and so I want to show you quickly how we can look at this. This here is again the example of a counterflow diffusion flame. We introduced this, what we did earlier. We introduced this similarity solution. I don't know why I have this twice here, but we introduced the similarity solution. And then what we can do is you can actually find under certain assumption basically that this rho times mu here, that is a constant. You can derive an analytic solution for the mixture fraction in the counterflow diffusion flame. And this is shown here in this example, but the result of this is that the mixture fraction, so this is an analytic solution for the counterflow diffusion flame, and the mixture fraction is the complementary error function of the similarity coordinate eta. That's basically what it is. Complementary error function is just 1 minus the error function. Okay? And so you see now, from this, I can also determine the dissipation rate, because the dissipation rate is something like dz by the eta. Okay? So I can take the derivative of this here, and then derivative of this, and from this then, and the square of that, and that gives me the dissipation rate. You see that depends now on eta. I can solve this here for eta as function of z, plug this in here, and then this is what you get. So it's the exponential of the inverse, so -1 is not 1 divided by, it's the inverse of that function, is the inverse of the complementary error function. So this is a complicated function here, but you can find an analytic solution of this dissipation rate. Okay? And it's not shown here, but this is how it looks like. So if you plot this as function of z, then it kind of looks like this. Kind of looks like this. It has to go to 0 for pure fuel and pure air, because once you're in the pure fuel, the gradients have to go to 0, and once you're in pure air, the gradients have to go to 0 there also. And the other thing you see here in the counterflow diffusion flame, the dissipation rate, that's what we said earlier also, is directly related to the strain rate. They're actually proportional to each other. Okay, so again, the strain rate is something you oppose by the velocity field, but that causes then a certain dissipation rate. So that function here, that is often used when solving the flame-lit equations. When solve the flame-lit equations, we often use this function here to specify the dissipation rate as function of this mixture fraction. Okay, so just like for the premixed flames, where you can do an analysis using thermal flame theory, one-step global reaction, you can also do the same thing for the diffusion flame. There is a classical analysis by Professor Lilian. He did this in the 70s. This is one of the most famous papers in combustion science, I would say. Is a great analysis. And this is what he finds basically, is that he finds that if you increase the dissipation rate here, then that's what we said earlier. The fuel, so this is fuel diffuses, so you have heat losses away from the flame, but at the same time, the fuel diffuses into the flame. And so basically, the temperature shouldn't change because you just consume a fuel while you lose more heat. But now you don't, if the dissipation rate is very high, then you don't have enough time to burn the fuel, and then the fuel is not completely burnt. And what he found was, from his analysis, that you have leakage now of fuel into the airstream. Okay? That's interesting, because from experiments, we know the opposite is true. If the dissipation rate gets very high, we don't have leakage into the air. We have leakage of oxygen into the fuel. Okay? So that, should just show you again. This is a great analysis, but the one-step model, it usually gives you, it's not the reality. It usually gives you something that's not quite the reality. Turns out the reduced mechanism describing the diffusion flame is the same as for premixed flames. That's interesting because it doesn't have to be the same. It could be that different reactions, other reactions become more important than for the premixed flames. But it's the same, and you see here also the fuel is radical consuming. Yes?
I was just curious about the statement that you just made. When we went through this derivation the other day, we based it purely on kinetics and the branching mechanisms that were important in this kind of thing. So could you talk a little bit more about, how could that be the case that these no longer are important because it's a diffusion flame instead of a premixed flame?
That what is no longer important? The reactions. Okay, so the one reason why the fuel consumption is radical consuming is that the methyl radical is consumed with O. Okay? So 1, 2, 3 radicals, 1 radical. You consume 2 radicals in this reaction. Could be that in diffusion flames, on the rich side, the temperature, let's say, is relatively high, and you have different reactions that consume the methyl radical. Could be that the methyl radical, it just decomposes. CH2 plus H plus N. Okay? This is not radical consuming. Okay? It even produces a radical. If that was the main consumption reaction, then this global step wouldn't be true anymore. Okay? But it turns out you get the same things. Okay, so this here is actually a simulation that was done with a 4-step mechanism. Well, you see this the temperature, and here you see that you have no fuel leakage into the. So these are 2 different strain rates. No fuel leakage into the air, but you have oxygen leakage into the fuel, and that's interesting because the analysis here that was done by Seshadri at UCSD identified then that actually the structure of these diffusion flames, although they're very different, in a sense you can compare it to premix flames. In premix flames we had 3 layers. We said we have a preheat region. The preheat region, that's the same here as this outer region where you have no chemistry, where just the fuel diffuses towards the flame and the oxygen diffuses towards the flame. These are chemically inert, okay? Really for 2 reasons, because again, here you have very little oxygen, here you have very, very little fuel, and secondly, the temperatures here are relatively low. So that's the outer structure is the same as the preheat region, let's say. And then you have the inner layer that we had for the premix flames. That's the same here. You have the inner layer now. Also here at stoichiometric conditions, that's where the radicals go to 0 basically, or the radicals are consumed together with the fuel, okay, where the fuel is converted into CO and OH. And then you have here on the lean side, you have the oxidation layer where then fuel and where then the CO is converted into CO2. So typically, if you look at the temperature profile, you see there's some curvature here in this profile. That is because this is the region where you have the CO to CO2 conversion. So let's see if we see this in the detailed chemistry simulation also. Yeah, here, for example, you see it also. You have some curvature here on the lean side, which is this conversion here. Well, it's hard to see, but you typically see some curvature here, which you know is just the signature of the heat release there. Okay, so this is what I just said. Then, if you look at the structure here, this just an example that shows this. This is the temperature here. Oh, so I could have just flipped one forward instead of 25 slides back. This is the temperature, and then you see this here is the production of CO. So you see here, in the inner layer, exactly where the temperature is maximum, that's where you form CO. This is the production rate of CO. And then on the lean side here, CO is consumed, and then you see on the lean side here, the CO is formed. And again, you see a slight curvature here in the temperature profile, okay? Okay, so that's basically says the same thing again, and that just here compares again some of the experimental data with the experimental data with the simulations using that model. Okay, any questions about this? So here we didn't want to go through. I didn't want to go through the details of this analysis. Just tell you what really what the main thing is that comes out of it is that the one-step reaction gives you fuel leakage, which is not right. Multi-step kinetics gives you oxygen leakage, and that is right. When is the break again? Is now, right? Yes. So why don't we stop then for a break, and we'll meet back in 10 minutes.